Hi, welcome back. What I have here is an R environment with all of the code through the end of video 5 executed. And where we ended up at the end of video 5 was we were able to create a nice clean data frame, that was populated with not just our term frequencies, but our TF-IDF transformed term frequencies, our mighty TF-IDF transformed term frequencies. And you'll see this here, right? Go and Jurong and point and so on and so forth. Now, what we learned last time was that in theory, TF-IDF improves upon our base representation. And our base representation, once again, was a document term frequency matrix, essentially for every document, just a count of the terms. And we talked about how, well, that's a very powerful model and it works pretty well. There are a couple of issues. One is documents of different lengths will, of course, have different counts. Longer documents will tend to have higher counts. And two, terms that appear frequently across documents, for example, hypothetically, a term that shows up in every single one of my documents isn't particularly useful from a predictive perspective. So we saw how TF-IDF actually addresses both of these issues in a mathematical calculation, and we use that to transform our data to get these values. But now the proof is in the pudding, right? Let's repeat our process. Let's repeat our 10-fold cross-validation repeated 3 times, building single decision trees each time, and see if in fact we can actually improve our model's performance as measured by the cross-validation process. So, no problem. We can go ahead and do that. Now notice, as before, I'm going to go ahead and turn the number of cores down. The code by default is set up for a big machine, a workstation or a server class machine. I'll be running this on my laptop, so obviously I don't have 10 cores on my laptop, so I'm going to turn it down to 3 and have this run on my laptop. Now notice that all the rest of the code is exactly what we saw before. I'm going to go ahead and use do snow again so that I can train in parallel. I'm going to spin up 3 instances of the cluster. Behind the scenes, I will run my training as before. Everything's going to be exactly the same. The only thing that's different is now I'm going to use our mighty TF-IDF weighted data instead of just the normal document term frequency matrix as we saw earlier. And then we'll go ahead and see the total execution time and our results. So I'll go ahead and highlight all of this code and get it kicked off and running, and then we'll come back once it is done. Okay, so we're back. So notice that the code this time took a little bit longer to run than last time, took over 10 minutes. No problem. Let's check out our results. So as before, R and Caret handled this process for us, and we were training a cart tree over 3,901 samples, or 3,901 rows in our data set. Each predictor contained a TF-IDF representation of our data, and we had 5,743 predictors. So we did 10-fold cross-validation repeated 3 times, so all of this is the same. Now notice that once again, our CP value that was the best out of the 7 that we tried was again the lowest, this one right here, 0.0133, so on and so forth. And notice that our accuracy is 0.9476181. Now that is not much, but it is higher in accuracy than what we saw with the previous representation, which was just a simple document term frequency matrix. So what this shows us is, in fact, we did get some uplift. We did get some uplift in using the mighty TF-IDF on our data. Okay, cool. So that's great. So we've got TF-IDF, but now what? Is there anything else that we can do to improve the performance of our model? Is there anything that we can do to provide better data? Because, as I mentioned before, garbage in, garbage out. Good data is the linchpin of creating a good machine learning model. So we spend a lot of time worrying about data representation and creating good features to feed into our models. So what's up next? Well, what's up next is something called n-grams. N-grams. So let's go ahead and talk about that. Okay, so we're going to revisit our representation. So this is the second time that we're coming back and we're going to revise our representation. So if you recall, our original representation was a document term frequency matrix. Each row represented a document. Each column was a term as a result of our data preprocessing. So tokenization, stop word removal, lower casing, removing numbers and hyphens and symbols, and then stemming. That was our first representation. Then we said, okay, look, let's TF-IDF transform that. That was our second representation. And now we're going to take a look at how we can augment this representation with yet some more ideas. So if you remember, we had a sample document earlier in the video series. If it looks like a duck, swims like a duck, and quacks like a duck, then it probably is a duck. Right? So we just use this as an example. And what we learned was if we ran this through a prototypical text analytics data processing pipeline, we would get something that looks a little bit like this. Look like duck, swim like duck, quack like duck, probable duck. Right? First and foremost, we lowercased everything. Second of all, we removed all the punctuation, and then we removed all the stop words, and then we stemmed, because obviously you can see here, probably became probable. The rest of these were not affected by stemming, but notice words like and then, and if and it, and were all removed. So essentially we get just the terms that essentially quote-unquote matter, or potentially quote-unquote matter. Look like duck, swim like duck, quack like duck, probable duck. And as you can see, even though it's not proper English, since we know what the original document looks like, we can actually kind of squint our eyes a little bit, and from far enough away we can say, you know what? Yeah, this representation, while not ideal, actually captures the essence of what the original document is trying to say. So cool. Now, we also could see that, great, once I got that, this representation here, right, this result of our tokenization processing pipeline, we can then say, okay, great, I can transform this into a data format that R can understand. We can create a document term frequency matrix, and we just count up all of the individual terms and just create a table like this. So we have 1 look, 3 likes, 4 ducks, 1 swim, 1 quack, 1 probable. Cool. Great. That's our document term frequency matrix. We then said, okay, look, you know what? Later on, we said we can TF-IDF it and make these numbers actually more valuable than just the simple counts. But we'll ignore that for the time being. So what we need to do is talk a little bit more about n-grams. So far, our representations, whether they are just plain old term frequencies or they're TF-IDF transformed values, are still about single terms, like duck, walk, quack, so on and so forth. In natural language processing and text analytics, these are known as unigrams, or alternatively as 1 grams, which makes sense, right? 1 gram. That makes a lot of sense. If I have a single term, the number 1, there's conceptual alignment between this 1 and single. Cool. In grams, you can just say, okay, are terms. Sure. 1 terms, 1 terms. Cool. Given that, though, it's probably your intuition, which would be correct, that there are, in fact, also more than just unigrams. There are bigrams, there are trigrams, quadgrams, quingrams, or 4 grams and 5 grams, you name it, right? You can have combinations that are more complicated. N-grams are cool because they represent an extension to our bag of words model to include word ordering. Now, this won't be as sophisticated, for example, as a full-blown grammatical analysis or a full-blown, language processing analysis of everything, of all the terms. But if we say, look, you know what, at the end of our data preprocessing pipeline, our tokenization, our stop word removal, stemming, removing of numbers, so on and so forth, we say, okay, great. We have the collection of those terms that we get out of the result of that process. We can still extend our bag of words model to include word ordering to maybe get more powerful features, to get better data, to provide more information, more signal to the machine learning model so that it can better understand what's going on inside the text. Okay, so let's see how that works. So let's add bigrams to our existing sample document. So here we go. So once again, let's take a look at our process data, right? Look like duck, swim like duck, quack like duck, probable duck. Sweet. So we already know what the unigram model looks like, so we won't worry about that because we've seen that ad nauseum. Let's talk about bigrams. Now, what are bigrams? If we actually do a bigram of this particular document, this is what we get. Look like duck, duck swim, swim like, duck quack, quack like, duck probable, and probable duck. Now notice that this is actually not particularly difficult to figure out what's going on here, right? Essentially we say, look, bigrams are just essentially take two things that are next to each other and make that a distinct token, make that a distinct term, make that a column in our matrix. Look like are close together, so notice we just use the underscore here to separate them. Look like, we just pivot, like duck, duck swim, swim like duck, so on and so forth, right? Now notice that like duck shows up more than once. So instead of creating a new column, we just add to the count, just like we did before, right? Like duck, like duck, like duck. We got 3 of them, so we got a count of 3. But notice we have individual columns here for all of these different combinations. And notice that while we get a lot of power out of a unigram bag of words model, bigrams actually potentially add a lot more power. Look like duck, duck swim, swim like, duck quack, quack like, duck probable, probable duck. So this is pretty cool, right? We can start talking about, okay, look, probable duck, duck probable, starting to infer something about the semantic of this document, and then you can see the quack likes, and then like ducks, and all that kind of stuff. Notice how this is more powerful than just the simple unigram representation, all right? Not surprisingly, word positioning, word ordering actually helps out. And as you can imagine, depending on your situation, bigrams will add a lot of power, trigrams could add a lot of power, quadgrams could add a lot of power, so on and so forth. But here's the thing that you have to be cognizant of. This is super, super important. Oops. If we add these bigrams, if we add this collection of columns to our original unigram model, we've more than doubled the total size of our matrix. Because if you recall, our original document term frequency matrix for this particular document was only 6 columns wide. We only had 6 distinct terms. We had look, like, duck, swim, quack, probably, right? We only had 6 terms. Only 6 terms. But now notice that we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 terms. So if we add them together, our 6-column document term frequency matrix now becomes a 14-column document term frequency matrix with our bigrams. So this is super important. This is super important. Adding n-grams dramatically increases the power of your matrix. It gives you a lot more power. More often than not, bigrams and trigrams and so on and so forth are going to make your models more accurate because they will learn more signal in your data. But there is no such thing as a free lunch in machine learning, and text analytics in particular. You pay for this extra power in a radical explosion in the size of your matrix. Not only that, but what you'll find, and we'll see this in a bit, is that not only do you pay the price in terms of a much larger matrix, right? You have a lot more columns, many, many, many more times columns than you had before when you start adding bigrams and trigrams and so on and so forth. But you also get this problem of sparsity. Most of the cells in your table, in your matrix, in your data frame, most of the individual locations are going to be 0. They're going to be empty because most of the time, most of the documents are not going to share the same bigrams. And as you add more powerful features like trigrams and fourgrams and so on and so forth, it's even less likely that the particular word orders that you get out of each individual document are going to be shared across multiple documents. So you get this sparsity problem, which is you get this huge matrix. It's very, very wide, lots and lots of columns. And most of the contents are 0. Most of the contents are missing. So you get this sparsity problem. Collectively, this idea of very, very large matrices and very, very sparse individual data elements in those matrices is known as the curse of dimensionality problem. Text analytics suffers from the curse of dimensionality problem in spades. It doesn't take much for a relatively small data set in text analytics to explode to a really, really big problem space in terms of your matrix size. So you have to be really super cognizant of that. Okay, there you have it. That's the basics of bigrams. Let's go ahead and go back to R and see how we can now enrich our current feature matrix with bigrams. Okay, so we're back in R, and let's see how we can add bigrams to our document term frequency matrix. Okay, so if you recall, way early on in our code, we had this object of train tokens, right? So if I actually go ahead and pull out 357, which is one of the examples we looked at before, this is where we had, right? We had our individual processing pipeline, the results of our text pre-processing pipeline, right? So we tokenized all of the SMS text messages. We lowercase them, we broke them up in individual tokens, we then stem them, we removed symbols and numbers and all that. And notice that 357 was essentially this text that talked about the website bubbletext.com. Okay, great. Cool. So we're going to go ahead and reuse this object, and we're going to use a new function from the Quantita package called tokens underscore engrams. And I'll pull that up in the help file here, and you can see here, over here, create engrams and skip grams from tokens. So we're not going to talk about skip grams. That's a more advanced topic. But we'll talk about, well, we have talked about engrams. So what this is the function in Quantita that you can use on a tokens object to add engrams to it. And notice, so we call the function and we pass in our tokens object, and we can see example of what is included in that tokens object down here. And then we say, okay, great. We can tell it, look, what kind of engrams would we like? So for example, if I just said 1, which is the default, I would get a unigram model, right? That's the basic bag of words model, unigrams. Now, if I do 1 through 2, I will get both unigrams and bigrams. Now, notice I don't have to do this. I could just say, look, just create me bigrams only, and I would just specify it this way. Or if I wanted to get really crazy, I could do something like this, which says, give me a model, return me back an object that essentially is unigrams, bigrams, trigrams, 4grams, and 5grams. But we won't go there because that, as I talked about before, that will radically explode our feature spaces we'll talk about in a second. So let's go ahead and run this code here. And now notice that what I've done, right? So this was entry 357 before we added bigrams, right? Credit, top, HTTP, bubble text, so on and so forth. And notice now, instead of 7 individual tokens, when I add bigrams, I now get 13 tokens. Notice how I get credit top and top HTTP, and then HTTP underscore bubble text, and then bubble text underscore renew pin, and pin TGXXRZ. Right? Cool. So now I've got my bigrams. This is great. So now that I've got that, I'm going to have to go ahead and do the rest of the pipeline as before. So here's what I'm going to do. I'm going to go ahead and highlight all of this code here and just let it run, and then I'll go back and talk about all the other stuff that we're doing, because this will actually take a little bit of time to run, because as we'll see in a second, our feature matrix is much, much bigger. Okay, so I'm just going to run that and go back and take a look at this code. Okay, so notice as before, we'll go ahead and transform that raw token object into our document term frequency matrix representation using the DFM function from Quantita. We'll then turn it into a plain old vanilla matrix as we saw before, right? This is just a base R matrix, so we can work directly with the numbers. I then actually invoke the actual DFM, so I get this output. So this is if you just type in the name of a quantita DFM variable on the command line and just let it run. This is the feature, this is the output that it'll give you. It'll talk to you a little bit, it'll give you a little information about how this DFM is structured. And here's the thing that we want to take a look at. So as before, we have 3,901 documents. But notice this. We've gone from 5,700-ish columns to over 29,000 columns. 29,000 columns. So we've gone up by more than 5 times, right? By adding bigrams, the number of columns in our matrix has increased by more than 5x. 5x. Now this is super indicative of that problem I was talking about earlier in text analytics, is that, excuse me, let's scroll back up here. So you will get radical explosions in your feature space using bigrams, trigrams, so on and so forth. However, they're often extremely useful in making your models as accurate as they possibly can be. And lastly, what I want to show out in this output here is notice that this is 99.9% sparse. And in fact, I'd be willing to bet that it's more like 99.999-ish. 3 nines past the decimal point, sparse. That is, the vast majority of locations in this matrix are going to be 0. They're just going to be 0. There's going to be nothing in there. There's going to be no values in there. Because think about this for a second. How likely is it that another text, an SMS text message, in our entire corpus of 3,901 text messages is going to have this exact combination of tokens, this exact combination of terms, HTTP followed by www.bubbletext.com. I mean, it's possible. I mean, these text messages come from the UK, and maybe bubbletext.com is a wildly useful and popular website, and people get lots of text from it in the UK. But I kind of doubt it. Probably even more germane is this right here, which is pin_TGXXRZ. This seems like some sort of code, and I would be willing to bet that there's a certain. It's highly likely that this code is relatively unique. So there is no such thing as relatively unique, but you get the idea, right? That this is not going to be common. Ergo, this will not be common. So we've just added things that are probably unlikely to be duplicated across our matrix, right? So these, this is another good example right here, www.bubbletext.com_renew. So that tells you a lot about what's going on here. We're radically exploding our feature space. But yet at the same time, we're not necessarily getting a lot of uplift in terms of data inside those individual cells, right? That's the sparsity problem. We'll potentially get a lot of predictive power out of this, but we're going to pay the price of huge numbers of columns where most of those columns are essentially empty. Okay, cool. Now you'll notice that this code that I wrote took quite a while to run as opposed to last time. And that's because this code is just plain old R code. And we've written it this way so that you get an idea of what's going on behind the scenes, but it is not optimal. So just so you know, there are plenty of libraries when you get serious about doing text analytics that have much more efficient implementations of the TF-IDF calculation than what you see here. And you'll be able to use those to accelerate your execution time. But here's the critical thing, and I've mentioned this before, and we need to make sure that you have this in your calculations, right? Which is you need to maintain whatever library you use, whatever package you use, whether you hand roll it yourself or you use Quantita or you use the TM package or whatever. When you do this and you calculate the IDF vector for your training data, you have to cache those values. You have to maintain that and store it somewhere. You have to have access to those IDF values. Because as I mentioned in the last video, and this is super important, and it bears worth repeating, you need these IDF values stored because as new data comes in, it is required to translate any new documents that you're interested in working with into the same space, into the same footing, into the same transformational area that your training data was located. That's the easiest way to think about it, is to think about it geometrically, right? We need the ability to transform new documents into the same TF-IDF space that our training data was transformed into, because our models will only understand documents in that TF-IDF space. So we need to have this data retained so that we can do that transformation. This is going to be super important because we're going to revisit this same concept when we talk about singular value decomposition, when we do feature extraction. This will be essentially the same idea. We're going to be projecting our training documents into a different space, into a different representation, into a different transformation. This will make more sense later, I promise. And our model will learn that. Our machine learning model will learn that because the only thing it can learn is the data that we provide it as part of training. So we need to maintain that data, maintain that that mapping, that transformation for any future data that comes in. So we have to, not only do we have to maintain the IDF vector for future data, but when we do singular value decomposition, we will also have to maintain those matrices that we get out of that operation for exactly the same reason, so that we can do the transformations. Okay, so the rest of this code is exactly the same. So what we get here is a clean data frame that is now a TF-IDF transform representation of both our unigrams and bigrams. Now, the last thing I want to show here is the GC command. Now, if you're not familiar with this in R, this is going to be super important when you work with text analytics. This GC command forces R to do what is known as garbage collection. This essentially tells R, hey, go in and free up any memory that you can free up. Now, periodically, R will do this automatically. It'll go through and free up memory that it doesn't need anymore. But as we're doing a lot of these calculations and these transformations, we're actually going to be using quite a bit of memory. So as you can see right now, my laptop has 16 gigs of RAM in it. Not too bad. But notice that right now, my RStudio session is using over 7.2 gigs of RAM. Now, if I run this line of code, you'll notice that that a bunch of stuff gets cleaned up. And if I go back, you can see now that actually it didn't help very much, which is a problem. Because this tells you very, very simply, like, I'm starting to stretch the limits of my laptop here in terms of working with this textual data. And that's something that's going to be pretty common. And that's something that we'll be covering in the next video, is that we'll see, okay, look, now that we've got this much larger representation, this 3,901 observations of 29,000 variables, we're going to start running into some problems. We're going to start running into scalability problems in our machine learning algorithms that we're using to do our work. So, but that we'll table that for next time. As always, if you have any questions or concerns, feel free to use the comments section on the video. We at Data Science Dojo monitor our YouTube channel frequently and try to answer all questions promptly. And if you like what we're doing here in terms of our tutorials, please subscribe to the Data Science Dojo YouTube channel. We will be publishing new content weekly, so that if you subscribe, you'll be able to keep abreast of the latest and greatest offerings that we have on data science. Also, even more generally, if you like what we're doing at Data Science Dojo, feel free to follow us on social media. We're on Twitter, Facebook, LinkedIn, you name it. And if you connect with us on social media, you'll get a nice steady stream of curated data science goodness. And lastly, I hope to see you in one of our upcoming Data Science Dojo boot camps. Until next time, this is Dave Langer, and I wish you very happy data sleuthing.